Welcome, everyone. My name is Marisa Gomez, and I'm the Public Programs Manager at the Santa Cruz Museum of Natural History. Tonight, we're going to be examining the CZU lightning complex fires from what I think is a pretty unique angle. The intersection of weather and wildfire has been on my mind since last year's storms, and I'm personally just truly eager to learn about this phenomenon from our speaker, Chris Giesige, who is here with me now, not literally, but in the Zoom room. Hello, Chris.
Hi.
Hi. Welcome. Welcome. Before I hand things over to you, I do just have a few notes. So tonight's program is part of the series CZU and You in partnership with Santa Cruz Public Libraries. Together, we are offering a month of programs meant to support our community as we remember the events of last year's CZU lightning complex fires by providing resources for recovery, preparedness, and ecological understanding. And we've already had several programs, a number of which we have recordings of that you can go back and watch if you were not able to join us for them. The first one was actually with the Amamutsin Land Trust. And so I do want to acknowledge that the fires impacted the ancestral lands of the Awaswas-speaking Sayanta, Yupi, Chitoni, and Ashistaka, and the Ramaytush-speaking Kuroste. And today these lands are stewarded by the Amamutsin tribal band who are working hard to fulfill their obligation to Creator, to care for and steward Mother Earth and all living things through relearning efforts and the Amamutsin Land Trust. And just once more, I wanted to invite you all to communicate with us throughout the presentation using the chat. And I see that many of you are already doing that. The lightning storms and subsequent fires impacted everyone in our community, and we want to hear from you as we launch into this presentation and conversation. And if you have not already, please take a moment to adjust who you are sending your messages to and select the option for everyone so that we can all communicate with each other. And let us know what you remember from last year's storms. Chris, I know that you travel around the country a lot, but were you in California last August for the storms and the fires?
Yes, I was. I'm living right now in Roanoke Park in Sonoma County. And if you're unaware, Roanoke Park is a city just south of Santa Rosa. So there's been quite a bit of fire experience in Sonoma County the past several years, but I was definitely around during the lightning event last year. And for us up here, it was very similar to what you guys experienced down there, or I'm sure what most of you experienced last year. So yeah, I was around, and I'm looking in the chat at some of the words that people are using, and a lot of you guys are right on, and definitely some of these words describe it exactly how you would, how you think you would.
Yeah, I love Kari's awful in the sense of awful. Like that's so perfect. That's the way I sort of felt too. Like I jumped out of bed and I rushed to the window and I was just like amazed in like a sort of positive way. Like, I don't know, part of me felt a little giddy and I was like hooting and hollering. But then, also like as the winds were howling and it just like kept going on and it was like so close, I also felt, very ominous too. So I relate with all of these.
Yeah, as from a research perspective, or for somebody who takes a look at fire weather and stuff, it's, we always say it's extraordinarily fascinating, and to me it's great, but it's not at the same time. Like, oh my gosh, the fire weather, the strength of the winds that come through, the strength of a lightning event that we just had, it's absolutely amazing, and it's really cool to look at from a research perspective. But from the other perspective of when it's happening, it's not great.
Yeah, you're in a unique position, and I can't wait to hear more about it. So I think we should get started and hear about your research.
All right. Well, okay, she introduced me as Chris. I, about 10 years ago, got together with my research associate, and started this group called West Cats. And so what we do is, I came from the fire science background, and my associate came from a background of, well, it's solar tech, technically, so electrical engineering within solar technology. But what he did is he got to monitor all these different weather events, because a lot of solar inverters, which is the thing that inverts on a solar panel that inverts solar energy to usable energy, they get struck by lightning a lot and they fry the systems. And so they spend millions and millions of dollars every year to put new inverters out there because they get struck by lightning. So he got to monitoring all the different weather events, and especially within the solar field, solar radiance, strength and changes in like magnetic fields and magnetic readings, but then things that we're more familiar with, like wind, pressure, dew point, and relative humidity. And so we started combining these things to start looking at either seasonal lightning patterns, and then the development of lightning within several days before an event, and how we're seeing this interaction between the atmosphere and the topography here on Earth in order to help give some sort of level of being able to establish and determine a high risk area, or an area that is of higher risk than other areas that surround it. So basically we've now gotten to the point where we're going out to several locations and we analyze topography. And these are locations that we think are especially high risk, just because of the type of atmospheric flow that they get there. So the type of wind flow that gets generated in those areas, or the type of shifting in pressure that we might see, but mostly because of the strength in solar irradiance and the way that that interacts with the topography, the layout of the land to create certain conditions for lightning and lightning events. So we go out to these locations and we are trying to collect data, because what we're trying to do right now is we have kind of a little small group of fire weather meteorologists from predictive services, and a few that we've talked with from the National Weather Service, to develop the sensor that would basically create another type of model, weather prediction model system for forecasting. And what we can do is use our model with their model as kind of a collaboration. So hopefully within our stuff, it brings better confidence to the models that they already have, because we're looking at things a little bit different than what the models typically look at right now. And we might be able to help establish a little bit better of an idea of how intense is an event going to get, or maybe where, what more general of an area might we see that intensity, or might we see that event, as opposed to what they're able to do with the models right now. So that's kind of where we are. And so hopefully soon these sensors that we're building get built, and predictive services has already kind of told us, hey, if you guys get these built, then you can just hook them up with our system, so we can kind of see as the proof that these things all correlate, and that they're going to be of some use for the future into better forecasting systems. So that's where we're at right now. And we face the inevitable conundrum and double-edged sword in science, where you got to have the data to get the funding, but you need the funding to get the data. So round and round we all go, right?
Cool. Well, what do you have prepared for us today, Chris?
So let's see. So I'll share my screen now. Is that okay?
Yeah.
All right. Move a few things around here. To do Just a second, get back to the beginning. And there we go. All right, so fire weather, fire weather and wildfire and lightning. Like we mentioned, terrifying and fascinating at the same time. And I'm sure most of you on here, in fact, many of us in California are very connected to fire these days. And that's because either we ourselves have experienced an instance where we've had to evacuate, maybe we've lost people, or we know somebody who has, and someone who has experienced these fires that we are experiencing in the past 10, 20 years or so. Hopefully nobody has experienced something like the recent fires in a shorter time frame than that. But something that's very interesting to me, and I hope you guys find very interesting too, is the weather that helps create these fire events. And something like the lightning events that we had. So I will be your captain, your skipper for the next 45 minutes or so as we take you through what fire weather is, what type of fire weather helped create the events for last August, and the event in the CZU lightning complex that most of you guys experienced last year. And then we'll kind of just transition to what are we looking at in the future, possibly with fires, fire behavior? What are we looking at with possible lightning events? And then we'll look at, I might end again with a little something about Westcats. So let's get started. This right here is our fire behavior triangle. So some of you may be familiar with the fire triangle. Is a triangle that says, okay, in order to have fire, we have this network. You have to have oxygen, we have to have heat, and we have to have some sort of fuel. Well, we have a similar triangle for fire behavior. And the fire behavior triangle consists of fuel again, as you can see on the graphic here. The amount of fuel, how the fuel is arranged, is it compact? Is it pretty thin? Is it spread out? And the moisture content of that, the live fuel moisture content and the dead fuel moisture content of that. And then something I mentioned earlier is the topography. And when we're looking at topography, we look at several things. We look at things like mountain ranges and the role that they play on the development of winds or the development of thunderstorms. We look at the slope. We look at the aspect of it, and that's just the side. Which way is that particular slope facing? We know that if it's facing more of the south or southwest for us over here, that it's more inclined to get stronger inputs of solar radiance. So we know the fuels are going to dry out a little bit quicker, a little bit more. It's going to be more warm on that side. And then, of course, here we are, weather. And weather is kind of the unpredictable factor here within the fire behavior triangle. And that's because we know the topography, we have a pretty good layout of it. For the most part, it's not going to change much. Fuels are tracked very easily. We know, are they dense fuels? Are they light fuels? Are they more grasses? We have a pretty good general overall understanding of the type of fuel that we're dealing with. But these little unpredictable weather factors can become quite the problem as they interact with fire or even help create some fires. So looking at things like wind shifts, unstable atmospheres, thunderstorms, fire created weather, all of this becomes a little bit less predictable than the other two aspects of the fire behavior triangle. All right, so what is fire weather? This here is just kind of an illustration that we have drawn up. I know it might be a little confusing because it's a little bit more in terms of what we look at as Westcats, But fire weather, we're looking at temperature. Is it hot? Is it cooler? Is it going to get hotter? Is it going to get cooler? Are things pretty stable? Is the atmosphere stable? Do we have something that is allowing the fire to move quicker? Are we getting big swaths of erratic wind coming in and pushing the fire in certain directions? Do we have an inversion layer, a warm layer that kind of sits at a certain elevation that prevents heat and things trapped underneath it from moving up? That's stability right there. But when that stability breaks, then we get inflows and flushes of much usually cooler air as it sinks, and then we get a little bit of erraticness within the possibility of the fire behavior. So that obviously was wind. We look at relative humidity. If the humidity is much lower, then fires like that. There's not as much moisture in the air to help kind of keep things wetter or wetter climates. And then of course, fire weather, a big one, lightning. This is what we experienced last year in August. And actually, we've had quite a few dry lightning events this year for some of the fires. If anybody is following the fires up in Northern California or Oregon or Idaho or Montana or Washington. So when we talk about fire weather, these are generally kind of the things that we're looking at and the things that we want. Oh, I forgot to mention precipitation. Okay, precipitation, big one. That's both precipitation in water and snow. You know that a fire season is pretty dependent upon the snow melt, the amount of snow melt, and how quickly that snow melts. So we know how those fuels or that vegetation is going to react to changes and atmospheric conditions. You know, do they have more moisture? Do these fuels have less moisture? We prefer them with more moisture, but when they have less moisture, that's when we start to get the, okay, hopefully things stay all right. So fire in California, and you guys, you might have heard, I know there have been a few other presentations and talks, so some of this may sound familiar to you or repetitive if you attended any of the other lectures or presentations here. But that's okay, because we as fire scientists like to drill things into people's heads and can talk for hours and hours about this stuff. So fire in California. We have kind of the main factors here. We have human-caused fires. That makes up about 95%. And then we have other fires that might be naturally induced fires by things such as lightning. Human-caused, we're probably more familiar with, unfortunately. There's arson, electrical failures is the big one going around these days. Campfires left unattended, fires started accidentally, debris burning, you know, the old-fashioned tossing the cigarette out the window. So those are a few things that we kind of look at. It could be construction. You could be mowing your lawn on a hot, windy day, or using the old weed whacker and kick up a spark from a rock that hits off that blade. And before you know it, you got your heat. There's plenty of oxygen out there, and you have your fuel. So if it's a really hot day and you're going to do some yard work that includes mowing or weed whacking or anything electrical, try and do it before 10 a.m. When it's generally a little bit cooler. So the type of fires that we typically see in terms of fire behavior or fire weather behavior is we usually have either plume-dominated or wind-driven fires. Plume-dominated fires we saw a little bit last year, and we're seeing this year too. And typically something is plume dominated if The rising heat from the fire, so really hot air likes to rise up, okay? Everything that's down here is usually less dense than the stuff that's up there because it's cooler. So this warm air likes to rise. This is a convective process. And the cold air likes to sink, advective process. So when a fire is burning through this vegetation, it gets really, really hot. That hot air likes to rise, and we get mixtures between warm and cold in fire weather and other types of weather. When warm and cool interact, very interesting things happen. But here, within a plume-dominated fire, we have heat from the fire gets lifted. And as it gets lifted, it starts to cool and to condense, very similar to clouds. And we notice these big puffy smokes, these big puffy clouds up there in the atmosphere. It looks like, something that just went off out of a sci-fi movie. And the issue with those is that spotting can occur in all directions. And spotting is when you have a main fire and then you might have, let's say, embers shooting off from the main fire, and a mile down the road or so, they land and they start another fire. And now we've got one main fire and we've got a smaller fire, we get a spot fire. Well, with a plume dominated fire, that's those little embers and that spotting can occur in all directions because there's no consistent flow pushing the fire in any sensible direction. Okay. Then with wind-driven fire, well, it's exactly what it sounds like. Big winds come through, gusts or steady sustained winds, 20 miles per hour. And you'll notice that smoke column is kind of shifting like it is in the picture down here. It's shifting towards one side, and that's because the wind is blowing it that way. Might it be a little, in terms of predictability, well, that's kind of tough to say because they're both a little unpredictable. But the problem with wind-driven fires is this fire becomes a function of wind speed and direction. So when we look at fires that have huge growth within a very short period of time due to 70, 80, 90 mile per hour gusts, then we get spotting, those little embers that can be thrown miles and miles ahead, maybe even six, 7 miles ahead of the fire. And that poses a problem because all of our resources are on the main fire front, and then all of a sudden you get a bunch of smaller fires happening in another direction, and you get to throw some resources on that. So we kind of distinguish between something that's plume dominated, big puffy cloud of fire smoke that then creates sporadic spotting, and something that's wind driven, a fire that's being pushed by the wind. And that creates a lot of spotting, maybe a couple miles down the road. And just in case you are unfamiliar with wind talk, we always talk about wind and the direction it's coming from. So if it's a northerly wind, the wind is coming from the north and moving to the south. If it's southwesterly wind, it's coming from the southwest, it's moving to the northeast. Next, that brings us to what is lightning. Sorry, I'm moving around my little window here so I can better see these pictures. So what is lightning? Well, as someone who studies lightning, I love to talk about it, and I'll be happy to talk about it right now. Lightning, there's a lot going on, and some of these things, may not quite, I don't want to say make sense, but it's very hard to picture electrical charges within a cloud, within the atmosphere, separating themselves and moving and connecting. But with lightning, basically what we have is, you can see on this picture here, that we get, let's say, warm air rises. This is due to this could be due to daily heating of the sun, from the sun to the earth. So that warm air starts to rise, and as it rises, it cools and it condenses. And eventually we start to see a cloud. We see a little puffy cloud called a cumulus cloud. And if we get enough of that updraft from the air down below and enough of it keeps pushing higher up in the atmosphere, then we start to get those clouds that start to stretch and they get really, really tall. And a lot of times you'll see a little anvil on them. I'm not sure if you guys can see my arrow, but if you can, you start to see a little anvil on them that'll kind of tell you the direction of where they're headed. So within the cloud, we generally have these blue little negative charges, these minuses, will move more towards the bottom of the cloud or the middle of the cloud, and these positive, these red plus signs, positive charges start to move towards the top. And we have a whole bunch of different cool things. We got all these electrons, we have all these different charged particles. These ice crystals are hitting each other in the air and they're knocking electrons around. And eventually you start to build up a static charge. Well, down below on the ground, we have what we call induction. This is electromagnetic induction. So if we have, let's say, positive, or we'll stick with negative charges that are sitting on the bottom of the cloud, what they do is they force the negative charges on the ground to push down below the surface, leaving nothing but the positive charges sitting on the surface. And that's because they want to connect and they want to neutralize themselves. They want to come together so that they can take all of their energy and neutralize it. So when we see cloud to ground lightning, that is some of these charges from the cloud reaching down to the charges that are on the surface of the earth. And you'll also see charges on the surface kind of reach up a little bit to meet them. Or we can have lightning that happens within a cloud. So you might have the negative and the positive interacting within the same cloud. And you won't see the cloud to ground lightning, but you'll see basically those flashes within the cloud. Or you can have it from cloud to cloud. So charges from one cloud shoot over to connect with the charges of another cloud. And in this process, as we get these updrafts and the thunderstorm really starts to brew, this thing's, it's getting big, it's getting good, it's a little angry. You will also get these really intense downdrafts. And that's just cold air just pushing itself downward and hitting the earth, and it kind of spreads out. And all of this kind of poses an issue in terms of fire and fire behavior. So it's lightning itself is pretty cool, if I say so. And it can get a little intense, kind of like we saw last year. So why are we concerned about lightning events and fire behavior? Well, lightning can start fires, especially if it's not accompanied by a lot of precipitation or a lot of moisture, or it's very dry outside. The vegetation is very dry. The moisture content in the vegetation is really low, is perhaps critical. So these storms come through and lightning provides the heat. Electricity provides the heat, then it hits the vegetation that's on the ground, and there's plenty of oxygen around. So something like a tree or maybe swaths of grass can ignite, and before you know it, we've got a fire. But we're also concerned from a few things. Thunderstorms also bring erratic winds. So if a fire is being worked on, let's say firefighters are out there trying to contain a fire, get under control, or watching it or managing it, and a thunderstorm rolls through. Okay, I don't know if any of you guys have ever been out when a thunderstorm comes through and you feel that huge rush of wind. It just feels like it's going to blow everything over. And even though it's usually a little cooler or much cooler, actually you'll see drops in temperature up to like 30 degrees, maybe even more sometimes when these storms come through. And you'll get this huge rush, the front or boundary that pushes just these winds that come pushing through. And the winds kind of act in an erratic behavior as they interact with the terrain and they interact with the topography. So if you're out working a fire and something like that comes through, then you're kind of looking at unpredictable fire behavior, because those winds are going to come in and just push the fire, and we might get little fire or wind eddies. So they might be in a bunch of different directions, and we're really not sure what's going to happen at that point. But we do our best to try and keep them aware on the fire line of what's going on. And then, of course, we have last year's events, dry lightning events. This is lightning with very little precipitation. Lightning comes through and just lights up the entire countryside or the entire state side. But then also something that's really cool but kind of scary about fires is that they create their own thunderclouds. I know there's a lot of talk right now about, or I've heard and picked up on talk about a lot of fires creating their own storms, and there was people just saying they weren't really familiar with this particular topic. So it's kind of the same thing. So as we look at this picture here from the Bureau of Meteorology, which is actually Australia, we get this fire, burns really hot, and that heat rises, that then cools and condenses as it goes into the atmosphere. And we get generally one plume. So you get like one cumulus cloud that sits over the fire. But then if that thing keeps going and we start to see a buildup of a second layer of a cumulus cloud, and that's when the fire starts to create its own thunderstorm. There's just so much heat. It's just pushing so much air that these updrafts, the wind and the updrafts shooting up into the atmosphere, can reach up to 100 miles per hour. And then we get almost the exact same thing that happens with a regular thunderstorm, where we get all these things in the atmosphere starting to mix, and we get these charges starting to separate themselves, and then the thunderstorm produces lightning. So essentially, it's a fire that creates its own thunderstorm that produces lightning. And unfortunately, the lightning is usually in areas a little bit away from the fire. So then we get a possibility of new fires starting. Sometimes there can be hundreds of strikes. Sometimes it can be hundreds of lightning strikes. Sometimes it may only be one. Sometimes it may not produce any if we're lucky. But the threat is definitely there. But that's another cool aspect that I'm very interested in with fire weather and with lightning. Again, cool to research, not so cool to see. So we generally have conditions that lead to an enhanced fire year. So if we take the fire weather that we've talked about, we talk about winds, precipitation, talk about lightning events, we talk about moisture, we talk about heat and humidity. This is what we're looking for when we're trying to assess how bad might the fire year be. And as a lot of people have probably noticed, fire season, this term fire season really has become a fire year, because I mean, there were fires popping up in April this year, and we really need to be all hands ready to go and paying attention all year round now. Fires burning into December, wind events that last, through the fall into the following year. So these conditions, drought conditions. What are the drought conditions like? Is it extreme? Is it low? Are there not any? Is it above average? Is it below average? Because those drought conditions feel moistures. If there's a heavy drought, then a lot of the vegetation and the trees don't have a chance to recover from maybe a previous year when there was no drought. So then we start to get high tree mortality. A lot of dying trees out there. This picture was in Yosemite. This was actually 2015, kind of in the middle of that big drought year, the big drought years that we had between 2012 to 2016, 2017. And it was amazing. We were out there for a workshop, and it just looked like a third of the trees out there were not in good condition. So drought conditions, heavy, leading to an enhanced fire year. Few moisture levels, again, little precipitation, little snow melt, not good. The vegetation depends on that. Sometimes we also get to build up of fuels, and you might have heard about land management practices already if you attended some of the other lectures. If we have a heavy buildup of fuels, that also isn't too good, because now we've got more fuel for the fire to burn, and the more fuel to burn, it can burn a little bit hotter, a little bit more intense. So we kind of are in this feedback loop situation of what do we do? We either have a drought where everything's really, really dry and ready to burn, or we end up getting good amounts of precipitation and snow, and now we've got more fuel growth. So now there's more vegetation out there to burn. Kind of fighting fighting a game that's hard to keep up with. And then hot conditions, seems to be getting pretty warm out there. I know we've already had a couple of heat waves this year so far in California, and last year was no different. So when the heat's high, the humidity will drop, and fires absolutely love that. And then, of course, we look at things like wind conditions. Might be more familiar with the Diablo winds, the Santa Ana winds, or the Sundowner winds have pushed a lot of these fires. So how are these all coming together to create an enhanced fire year? Do we have a bad drought? Are the fuel moisture levels low? What do the buildup of fuels look like? What is the heat situation? How is that influencing humidity? And then what type of wind events might we have? So from all of that, from those conditions, we always see either CAL FIRE or the National Weather Service puts out these maps that have different colors on them: red, yellow colors, orange sometimes. And these are the fire weather watch and red flag conditions. And they are defined from the National Interagency of Fire Center. Fire weather watch, and I'll just kind of read here. Fire weather watch is a high potential for red flag conditions within the next 12 to 72 hours. So it's like, okay, we're confident we're going to have red flag conditions soon, but maybe not. So we'll just kind of bring up a fire weather watch, so we can take note of that. But then if it builds, it'll build into a red flag warning. And we see a lot of these throughout, especially the fall months here in California. And a red flag condition is met when we either have relative humidities between 29 to 42% with sustained 30-mile-per-hour winds or more, or if the humidity drops down to around 20 to 30%, then we only need 21-mile-per-hour sustained winds or higher. Or if the relative humidity gets below 20%, then it doesn't take very much wind. 10-mile-per-hour winds, sustained 10-mile-per-hour winds are enough to push a fire and do a little bit of damage there. And then, of course, the dry lightning events. There's a huge red flag warning. So we saw that last year. And dry lightning, just to kind of define it, is lightning accompanied by little to no precipitation. Here in California, if it's less than 0.1 inches of precipitation, then we can consider it a dry lightning event. All right, so what did we have going into this? Into the August 16th event. In the beginning, this is what drought looked like. So over here in California, as you might anticipate if you're not familiar with this, darker shades of red are areas experiencing exceptional drought, and lighter shades closer to the yellow, not as much drought, but still abnormally dry. But between 2012 to 2016, tailoring in 2017, that's when we had the excessive drought here. I mean, I don't know if you guys remember. I'm sure you probably do if you're living in California or anywhere in the Western US, but it was dry, a little precipitation, and it did not help any of our fire conditions. And because of that, tree mortality between 2010 and 2019 is 163 million trees dead, according to US Department of Agriculture. And when that happens, if you guys have heard of the bark beetle infestations, they're basically these beetles that love dead trees, come over and they take over, and it kind of makes things even worse. But 163 million dead trees, that's a lot. But if we're looking at a couple of days before the August 16th event last year, we really didn't have that bad a drought. It was up there, but it's not like this year. This year's been the drought monitors this year, if you guys have been paying attention, have been pretty intense. And then we also have live fuel moistures. So these are live fuel moisture levels. We look at, in red is kind of the minimum fuel moisture levels for those time of years. And then the blue is the current, and the gray is the average. And this is by month. So if we look at around August 16th, we can see from this blue line that the fuel moisture levels for the 100-hour fuels, it wasn't too far below average. They still dipped into that critical point, but it wasn't too far below average. And we've seen some this year that have been pretty low, even down below the red minimums that you see on this chart. So when we look at field type, we measure 1-hour fuels, 10-hour fuels, 100-hour fuels. 100-hour fuels are usually heavier, more woody type of fuels. And once these fuel moistures get down to like 50 to 80% of the fuel moisture levels, then we start to consider it critical. And unfortunately, what we had last year is we had this very timely spring snow and precipitation event. So it was dry, and then right there in the spring, as we make that transition into spring, we get a lot of precipitation and we get some snow. And what that does is it gives just these vegetation just enough to come alive, just enough to create some sort of fuel growth. So that when we have the event, it's ready to take off. And then something else that was happening the 16th of August beforehand are these energy release components. And energy release components, this is the available energy per unit area within the flaming front of the head of a fire. So basically, how hot is the fire going to burn? This is what it's measuring. How hot is this fire going to burn? Well, we can see that the energy release components, the ERCs, again, this blue line was the current state, and the gray line is the average. It actually wasn't too bad for Northern California, compared again to this year, but still we would like to see it lower. So we have drought, we have a little bit of drought, we have some high amounts of energy ready and available to burn, but it gets worse. So now we get that heat a couple of days before we start to get those heat that's coming in. We're over 100 degrees down in your guys' area and in Northern California, even towards the coast. It's in the 80s, some areas in the 90s, some closer to 100. And they're expecting more high temperatures on the way from the possible next week. The humidity was below that 20% mark. So that red flag warning that says, okay, 20% is pretty critical. We definitely reached that. And then it was below 10% in some areas, which is even more critical. So we had the driving force, timely precipitation in the spring, fuel growth, things get really hot, they start to dry out. But there's one more thing, and this was the kicker for the event. It's this tropical storm Fausto. and this monsoonal moisture. So the image up to the left is kind of how it started building down in the Pacific southeast. And as it built, it just kind of sat there. And then what happens, if you look at the picture down below, is you see kind of these remnants of it moving in towards California. And this tropical storm was just pumping moisture into the atmosphere right over California. And all that extra moisture makes it more possible for lightning events to happen. And then you couple that with the high heat and the low humidities that are in the lower levels of the atmosphere. And that's when you're going to get huge dry lightning events. So these are the red flag warnings issued for the 16th, the 15th, the 16th, and even later into the 17th and 18th. You can see red flag warnings for almost all of Northern California, inland and on the coast, which is huge for a single day event like that. That's a pretty big red flag warning. So these are the events. This image right here shows you all of the lightning strikes that occurred within the 3 to 4 day period. I think 4 days. But these were all the lightning strikes that came over California and the Western US. That is a lot. I mean, there's so much they're even overlaid and you get some dark spots in here. But that is a lot of lightning. So what we had is in total, this was over the 5 days. In total, there were 16,832 lightning strikes. That's on the left side. This picture on the left side, all those blue little dots, lightning strikes, over 670 wildfires. That's the image on the right. All those red dots are fires. There's kind of a general rule, approximately 1 in 10 or about 2% of, somewhere between 1 in 10 or 2% of cloudy ground lightning strikes will result in a fire. But Cal Fire, the issue is Cal Fire by itself had 585 fires start within their jurisdiction. And that's when things start to get overwhelming. So we have just all this lightning strikes, 16,832, 670 fires started. Crap, right? There's no better way to put it. Crap. The image on the left is large fires in California as of August 24th of last year. Most of them started that 16th, 17th, 18th. Some of the major fires were the LNU lightning complex up here towards Napa, the August complex in Mendocino County, the North complex, the SCU lightning complex, and these are some big numbers. These are some big numbers in terms of structures. Structures gone, some deaths there. The acres, yeah, there's going to be a lot of fires that are big acres, but we're more concerned about the structural loss and the deaths. And then, of course, the CZU lightning complex, closer to you guys, but sure most of you in here are probably more familiar with. So let's just take a look at this. The Santa Cruz, San Mateo conditions, and you'll notice a lot of similarities between these conditions and the conditions that we talked about leading to a bad fire year. Santa Cruz Mountain only had 16 inches of rain. You average 40 to 50. That in itself is going to create some pretty enhanced fire conditions. 60, that's very small. That's very small. Talk about not a good year for precipitation, some drought. And then, of course, the temperatures that week and the temperatures in the following weeks, 90s to 100s, like in the slide before, heat them up and get them ready. You're not getting the coastal influence at nighttime to cool things down, to bring the humidities up. So now you have no overnight recovery for these firefighters trying to work. The fire's going to continue through the night, no slowdown. Your humidity is there in those areas during these events, 4%. That is extraordinarily low, 4%. And in the Santa Cruz, San Mateo area alone, you guys had 300 plus or more lightning events. That's crazy. 300 plus lightning strikes, 27 confirmed fires. And because CAL FIRE had so many fires and so much going on at the same time, there's just a lack of resources. Every unit was dispersed. And all of the engines. So basically what you guys saw down there for the lightning CZU fires, you have 5 large fires pictured here on the right. The Warrenella, the Waldell, and then these 3 fires up here that eventually merged to create the CZU lightning complex. So an issue is these fires are in remote, difficult to access areas. It's hard to get personnel and it's hard to get resources up to some of these areas where you don't really have, you can't really get in there. Just either steep terrain or heavy fuels, it can be tough. Luckily at the time, there's some slow rate of spread. ROS stands for rate of spread, if you've heard that term or not. Only the understory was burning, so that's all the vegetation below the treetops. But then once the fire gets into the tree canopies, then that's considered crowning. So a fire is crowning if the treetops and the canopies are burning. Those first days, there was no crowning, just the understory was burning, low rate of spread. But limited resources. Every resource out there for CAL FIRE was booked. They were out working all the other fires and trying to respond to the fires you had. So there's plenty of time. There was good enough time so that these fire departments knew and these fire agencies knew that they were probably going to have to respond to something, but there's no resources, so there's no relief. And so everything's going okay, it looks manageable, and then all of a sudden 2 days later, this happens. August 18th, fire behavior becomes plume dominated. The fire increased. You start to see this large plume. I'm sure a lot of you guys saw it if you're in the area. Skies were smoky all up and down California for, it seemed like 1 to 2 months of just full smoky skies. They had spotting that occurred 6 miles ahead of the CZU fire. That's just trying to respond to that and trying to get resources to that many different spot fires around is a lot. And within that one day, 43,000 acres had burned. That's a big push. That's a big push within pretty much a 24-hour period of time. And those conditions were made possible by high heat, low humidity, plume dominated, and some wind. So in summary, you can see over here the map of the burn area and some previous fires that are in there. The CZU lightning complex was the largest one in the area in terms of history. And again, it's okay if it's just burning fuels, but once you add in the 1,490 structures destroyed and trying to evacuate the 77,000 people, it just gets really tough. And let's not forget the one fatality, a civilian fatality they had there. So this is a big fire, especially for you guys down there. This was big, and it was hot. It was dry. We had this tropical storm pumping a bunch of moisture in. So we had all these lightning strikes coming through California, 300 or more in the area of Santa Cruz and San Mateo. And it was just prime conditions to create this fire and the rest over California. So the fire behavior of 2020, we saw a lot more fire behavior other than just the ones in the complex. This is mostly due to the lightning events, the buildup of fuels that we're seeing, and some of the wind conditions. There were a lot of pyrocumulonimbus clouds. Those are the clouds that produce lightning caused by fires. And we're not used to seeing so many of these. We're not used to seeing so many pyrocumulonimbus clouds. Pyrocumulus clouds, yeah, they're, we'll see them quite often. You'll see them often just doing prescribed or controlled burn. But the pyrocumulonimbus, there was a lot of development of pyrocumes last year. And we're even seeing quite a bit this year. And then the fire whirls, it seems like nowadays every fire out there is producing a fire whirl, not quite a fire tornado, but the Loyalton fire last year did produce a true fire tornado. There's only been a handful in the history of us recording and being able to use the technology to keep track and know that something's a fire tornado, because it has to fit the definition of a tornado. So most of what you see are fire whirls or convective rotating columns. But the Loyalton fire was a fire tornado. And the cool thing about that is that the National Weather Service actually got a tornado warning to issue for that particular area. So they saw it on the radar, and they're thinking that might be the first time that's ever happened, which is kind of cool from the research perspective. And then just huge amounts of critical fire behavior. The Creek fire up in the Sierras, Northern Sierras last year, where they ended up evacuating all those people from the lake. We're starting to see this this really enhanced fire behavior that we're just not quite familiar with, and so it causes a few heads to turn, and people all over to kind of realize, all right, what's going on here. So what do we expect in the future with lightning and lightning fires? Well, we're not really sure with lightning. We think that these tropical areas, if the oceans get warmer and more moisture is being able to get pumped into the mainland, then, we should see more lightning events. We could possibly see that up in the Arctic too. But we're just not sure. Right now we're not really sure. We're going through a few changes. We're going through a lot of changes, and we still need to monitor that, and more research needs to be done, and we need to see if we can try and wrap our brains around it. But the suspect is, because more of that moisture could be pumped in from the ocean, and we might see the changes in the development of the pressure patterns, that we might have some more lightning coming through the area. I know there's been quite a few lightning events coming through this year. And if the lower parts of the atmosphere that we're in continue to stay hot with low humidities, then we might see some more dry lightning events. But honestly, we're not too sure at this point. The fire situation, yeah, fires could get worse. This little graphic that you guys see kind of explains how when things get hotter, things get warmer, we start to see more extremes. So even if we do see more precipitation, it's probably going to come in the form of extremes, so extreme downpours. But we're also probably going to see some more extremes in temperatures and humidities. The snow is going to be melting sooner, so our fire season could possibly, continue to expand as the fire year grows. And that's kind of where we are. We expect our fire years to continue to look maybe somewhat like they have in the past. We're hoping that we can get together and make the changes that need to be made to help mitigate that. But we do expect to see possibly a little bit more lightning events. We do expect to see maybe some more climate induced fire behavior and fires going forward in the future. So what do? We try and communicate, try and tell people, what's going on, awareness around the fire situation. And right now, the big thing, as you might have heard, is, good fire. We need more good fire on the ground and less unpredictable fire, that bad fire. And we need to manage it better. We need to make sure that if fire is burning in an area where it's okay to burn, let it burn. But we also need to help contain those boundaries in which fire is starting to protrude into the so-called wildland-urban interface, where wildland meets urban areas. And for us on the fire weather side, continue to try and do better understandings, build better forecasting models. But overall, we need more cohesiveness between the local agencies, tribal agencies, federal agencies, and state agencies. WESCATs, what's the role we might play? Well, we might be able to tell you, okay, last year's events, this is what the intensity is going to look at. This is how confident we are. This is how confident you guys should be. Some of these wind events, how confident are we this wind event's going to be at this level? Or are we going to see it at higher levels? So the role we'll play as WESCATs is being able to kind of nail down how intense we think these events are going to be, which can then help for development and allocating resources, making sure things go well. I think I've talked probably long enough. That kind of concludes at least what I wanted to say within the short period of time. I know each one of us researchers and communicators could talk for hours about this stuff. There's a lot to wrap your head around. There's a lot to look at. Hopefully that was kind of a good general overview of what we look at with fire weather and the development of the events that happened last year. That was an extraordinary event to have that much lightning in California during that time of year, to create those type of events from those conditions. That was pretty extraordinary. And there's going to be a lot of looking back on last year and brainstorming and looking at how we can figure more of that out, and how are we going to be able to have better predictive measures and forecasting measures for those types of events in allocation of resources. So that's it. Thank you. Hopefully everybody stayed interested. I know it can be tough.
Oh no, definitely. This is fascinating. And yeah. I mean, based on what you just left us with too, so is it really that there was that tropical storm, like that was kind of like the outlier piece? Like sometimes we get super low humidity coupled with super high temperatures, but really it was like that tropical storm remnants were coming through that provided the cloud aspect. Was that the kicker?
Yeah, the having tropical storm Fausto and the moisture coming in from those areas was really kind of what set this off. Yeah. And we had the first event that first weekend, 15th, 16th, 17th, and 18th, it lined up. And if you guys remember, there was another one that came around, but it wasn't quite as powerful. But we still saw a few strikes and a few fires start. But having that tropical storm down there just pumping in, I mean, it looked like it was shooting a ray gun of water and moisture at California, just nailing us. And that was the generator, kind of the generator of the whole thing. And everything leading up to that was just, all right, we're getting ready for this event. And then the tropical storm was, okay, the event's here.
Yeah.
If that makes sense.
Yeah. Did you guys experience up in the Santa Rosa area, the roll cloud that we got down here? Did you hear about that?
I don't remember.
Do you know like about that phenomenon? So a lot of us who stayed up to watch the storm, I think like saw this happen where there was this massive like push of a cloud. So it wasn't like a gust of wind. It was like you're looking at this like this strip of cloud that came in. And it was a very odd experience. I was just curious if that had anything to do, if that was just like a secondary phenomenon that kind of like wasn't connected with the lightning aspect, or if there is some sort of connection there.
It could be, yeah. So if you guys saw it, if you get just huge fronts like that are pushing through, and you can see that's telling you there's some sort of interaction going on between the atmosphere and the earth. And so when you get those strong pushes like that, you see that type of cloud, and it's pretty much an indicator that, yeah, something's headed your way. It's not necessarily the driver of the event, but it's an indicator of, okay, yeah, here it comes.
Yeah, that there's a lot of activity going on.
Yeah. They're again cool to look at, but
yeah, no, it was. I mean, again, like that for all of us watching it, it was super cool and then super terrible. But we did have a couple of questions come through too. Someone was curious about the live fuel moisture levels section. How do you measure that? Like what the moisture level is within the fuel?
So there are several ways you can do that. One is called weighing the load, and that is basically when you take fuel samples and you bring them into a lab and you weigh them. You can kind of weigh like a before and after, and that'll give you an idea of how much moisture was in that. And that kind of gives you an idea of the fuel moisture content, for that particular time frame. I know there's some devices that you can stick in a tree and it'll give you a fuel level reading. But we also use a lot of satellite. There's a lot of satellite imagery that'll kind of tell you the state of the vegetation based off of what kind of frequency is getting bounced back from that vegetation.
Oh.
I
assumed you were going to say color.
Yeah, I mean, and that relates to the frequency. So that color that gets bounced back is connected to a certain frequency. So when those instruments up there, they send out a pulse, and then they hit whatever material it is, and something bounces back, and it shows you a color, and that color is just to a certain frequency. So that could let you know too what type of state the vegetation is in.
Wow.
Yeah.
Okay. And so who measures that is a question that just came in.
It could be fire agencies, weather agencies, people maybe. So the fire agencies would do the on the ground measurements, or if you guys are all familiar with San Jose State University, they do that kind of stuff there too. They'll measure fuel moistures within the area that they kind of monitor.
Yeah, I know. I saw that a professor of the fire program there is in the audience. So.
Oh, really? Who is it?
She knows more about that.
Yeah. She definitely.
Yeah.
It'd be cool if we were in person to have them talk about it instead of me.
I know. Yeah, this is still lovely though. It means that we get to talk to you when you're in Santa Rosa.
Oh, I see.
Yeah.
That's you, Amanda.
Oh. Sorry to do that, Amanda. Okay, we've got some other questions too, really quickly, and then we'll let you go. Justin starts his question out by saying, "Excellent presentation, by the way. I have a question. Could you perhaps explain the process behind cloud to air lightning? Do air parcels in the atmosphere also carry electric charges, allowing lightning to come out of the cloud?"
Cloud to air. I'm assuming he means like cloud to cloud.
I think he's meaning like maybe, but the way I read it is not cloud. Like is it possible for it to go from a cloud, not down to the ground, and not over to another cloud? Is it possible to just go out?
If it's going out, it's looking for a charge that's somewhere else in the atmosphere. And usually that higher charge is within another cloud, or it's on the ground, or it's within its own cloud. And the cool thing about it is, you guys notice the little streaks? So lightning, you see the streaks, it's all streaky. That's because those charges are trying to find each other. So they can't really sense exactly where each other are at. They don't have, their GPS system isn't totally tracking, but they are able to jump a certain distance and then go, okay, maybe they're over here. Okay, maybe they're over here, up until finally they find each other. So you'll get that jaggedness.
This kind of reminds me of what is it called? Minesweeper, that game we used to play on the old computers. Do you know what I'm talking about? Yeah. Like where you just kind of like try, not this way, okay, this way.
Yeah. But if it's heading, if you see it just kind of go off into a random direction into the air, then it's basically just trying to find its way to neutralize itself with some other stronger charge that's out there.
Okay.
Yeah. If I'm sorry, I hope that answered your question.
Yeah, I did for me. Kari is also wondering, any idea how tree mortality due to sudden oak death figures into this equation? You mentioned the bark beetles. How does sudden oak death compare to the beetle damage? I guess, do you have like a sense of like what the big players are for mortality of trees as a fuel source?
So, I mean, if you're looking at drought conditions, that's a big one for tree mortality. The bark beetles and the beetle damage, that's I'm not. I mean, I know about it and I know that it happens, but an ecologist would probably be a better one to talk to
Yeah.
about that, or someone who studies it.
We'll look
But for
into
tree
it, Kari.
mortality, the long bouts of drought and precipitation is really what's going to enhance that tree mortality. But yeah, sorry, I hope maybe you're able to come across an ecologist who's more familiar with that.
Yeah. Someone also asked about our rainfall for the Santa Cruz area for this fire season. I was just trying to pull it up, and I have not yet done it, but you were
Okay.
at least indicating that we have had a worse drought year this year than the year leading up to the CZU lightning.
Yeah. Over in California, it's just, I mean, we had so little rain in California this past year. In terms of the Santa Cruz area, yeah, I would have to look at that up too. Sorry, I've been kind of away during the majority of this year.
So you work a lot in like Utah and Idaho, other states, right?
So we generally kind of, so what we do is we monitor maximum points. We deal with maximum points and solar irradiance, and how that might change up the magnetics of an environment because it interacts with the topography. So we go out, we kind of monitor that whole, as the irradiance kind of comes in the US like this, starts over here, maybe towards Florida, then it gets stronger here, then it goes up to Washington, then it kind of comes back down. So we mostly monitor that curve area, which is New Mexico, Arizona, California, and up, is kind of our main focus. But we've also gone out to Oklahoma and up to Washington. So that's mostly the area that we cover, and we're strictly looking at interactions between irradiance, atmospheric conditions, and topography, because we want to know the strong points of where we're going to put those sensors, the specific sites of where those sensors are going to give us the best readings. But in terms of I've been lacking this year with everything fire, except for reading what's been going on, because I've been visiting with some family and stuff. So exactly what's going on this year for Santa Cruz, I would have to look that up.
Yeah, me too. And we'll get that out to you guys. I can put it in the follow-up email that I'll send out probably tomorrow. And we just have one other question that one other question I want to get to, and then we'll let you go because we're kind of going over time. Or actually, Kari's sharing that my understanding of the fuels reduction programs developed by CAL FIRE, which are being adopted locally, is that they are based on forest models. However, they are being applied to all plant ecosystems, chaparral, grassland, etc. I have concerns about that one size fits all application. Can you comment on this?
Yeah. Hit a big topic
to end on.
Yeah, you hit a big topic there, Kari. So the fuels reduction program right now, you'll probably hear a lot of talk about the fact that we've got ourselves kind of in a situation in California where land management practices haven't been the best, and that goes right there along with creating certain types of fire behavior and fire conditions. Yes, you would not typically want to apply it as a one size fits all. So there's a lot of interaction going on, at least what I see from the fire scientists who deal mostly with with, say, prescribed burning or treating applications is trying to get these different agencies on the same page and trying to do it in a manner that makes sense. So not just going out and burning things for the sake of burning things, but doing it in a strategic fashion, right? Which makes sense. But the one size fits all application is not what you want to see. It's typically not, just because certain areas are different. But there does need to be, we do need to have better land management practices, and that's going to include the tribal burning and cultural burning. You do need to have some sort of thinning, but you don't want to be completely logging areas at the same time. And you don't just want to, it's hard to just do nothing, because then we get buildup of vegetation and buildup of fuels that we have seen that cause enhanced fire behaviors. So, it's kind of tricky, because what CAL FIRE is doing and what the Forest Service is doing, and then what the tribal communities want to do, versus some other resources that are, or agencies that are kind of like, well, let's do nothing and just let the fire do its thing. It's hard to get all of those people on the same page, and it's hard to create some sort of cohesiveness there.
Yeah, and it's a complicated. I was just going to say, it's a complicated backdrop for all of it too. I'm just thinking about what you shared about how few of our fires are actually lightning induced and how many of them are human induced. But then also you've got the human element of having changed the landscape and altered how these areas that are then burning are managed. Yeah, it's complicated.
Yeah, and last year changed a lot, right? Because of COVID, last year changed a lot. So the Forest Service and other service agencies kind of went back to this. Okay, as soon as fire hits, we want to try and put it out quickly, because we want as little personnel responding. We don't want a lot of fire personnel in base camps where there's hundreds of them at the same time, because if one of them catches COVID, then their entire crew has to sit out. So they've kind of gone back to that response that the Forest Service initiated years and years and years ago. So COVID has kind of changed that, but generally lightning fires happen in remote areas were okay. Last year is an exception, because there was a lot of threatened structures in life, and it's always life, property first. And but the integration of populations, and where that they call the WUI, the wildland urban interface, you'll hear that term a lot. We're trying to figure that out. It's okay, what's the best approach to it? And there's a lot of talk about what the best approach is, but hopefully something is done soon. And we know pretty much that, okay, we need to start hardening homes to get ready for fire. We need to start managing and taking better care of the forests and the rangelands and the wildland. And that's being preached by a lot of fire scientists right now. We just got to get the state and the federal agencies in the same realm, and to do that, but it's tough. It's tough. I'm glad I don't have to make those decisions.
But and we've been having a lot of programs thinking about fire ecology as of late, and I've gotten to talk to a lot of different people with different perspectives. And one of the things that came up in a recent walk in a conversation was that oftentimes there's like a small window after a fire event to sort of have maybe interest focused in these particular areas where you can start to make change, and then it kind of fizzles out. But we're actually seeing, the perspective that was shared is that we're actually seeing, since there's so many frequent fires and so many large fires, and it keeps happening year after year, that kind of interest is not waning. in the same way. And so maybe we are kind of like on the precipice of some major changes.
Yeah, it's tough. I mean, we're exposed so much to all of the really enhanced events that happens, because that's what captures our interest. And maybe we can start getting more attention to, what's considered good fire. But there's been so much in the past few years with some of these big fires coming through and encroaching into communities that it's hard to separate that, unwanted fire versus wanted fire.
No, it's very true.
And to get that perspective out there.
It's very true. Okay. So this last question that came in was, is there any good news? So let's actually just end on that one.
Oh,
do you have any good news to share with us before we go?
The good news is we're doing a lot about it. And the good news is the highest minds in the scientific community are on this, and we know what needs to be done. We know where it's at. We know where the research is. We know the changes that have to be made, and it's getting there and doing it. So there's always an optimistic view out there that we're that close to doing such a better job. But we know what we're doing, we know what needs to be done, and we know how it needs to be implemented. So that's the good news.
Yeah. And I'll just share too that we sent out an announcement today to like our newsletter followers. If you don't already subscribe to our newsletter, do so. I'll include a link in the follow-up email. But like one of the questions we asked was, what role do you play in the future of fire in our region? And I think that for like all of us feeling so connected to it now, like since it's touched everyone who lives in California, basically, that there's a lot of ways that we can become more educated, have better understanding, and then help out in our own ways. So find opportunities to, if you feel passionate about it, if there are certain changes you want to see, there are ways.
Yeah, absolutely. It's sometimes the problem pushes an answer, right?
Yes. Yeah. All right, so I am going to be sharing again a follow-up email with the link to the recording for tonight's presentation, probably tomorrow, along with some resources from Chris, some of the ones that he listed in that last slide, and some other resources. So be on the lookout for that. There will also be a link to a survey, and we'd appreciate if you took just a moment to give us some feedback. And if you like what the museum's doing, consider becoming a member with us. That's how we are able to put on programs like this. And just thank you so much, Chris, for sharing your expertise and your time. This is really fascinating.
Yeah, of course. No, thank you so much for having me. And just the last thing, the sources is one of them is actually a talk from someone in the CAL FIRE Santa Cruz San Mateo unit, and you'll notice maybe a few similarities. But if you're looking for a more in-depth talk about the fire situation from last year within those within Santa Cruz and San Mateo counties, give that one a watch. He does a great job. He's got some great slides with great information and goes into a little bit more detail about what CAL FIRE was doing in that situation. And the other one is a great PowerPoint put together, not PowerPoint, but a great presentation put together by some National Weather Service employees that take you through the biggest stages of last year and the involvement of the National Weather Service, and kind of give you an account of a step-by-step for each one of those main fires. But that looks at California, the Oregon fires, Colorado, multiple of them. So it's really well done and well put together. So hopefully.
Well, yeah, and I really appreciate how much you focus too on on the warning systems and how important that is, and so I appreciate your research too, and getting us to a point where we can better understand what's coming. And wish you all luck in your work.
Thank you.
All right, so when I kick everyone out, I'm kicking you out too, Chris, but thanks so much.
All right, yeah, thanks again, Marissa. We'll talk to you guys later. Have a good day, everyone, or good night.